Hello, all right. Good afternoon, everyone, and welcome to the seventh session of Quantum Computing and Blockchain Lecture Series and Hackathon, brought to you by QCSP or Quantum Computing Society of the Philippines, also known as One Quantum Philippines, with DOST-ASTI, with a Project Shara in collaboration with DLSU Manila, College of Computer Studies, Department of Computer Technology, and this year, we are celebrating the International Year of Quantum Science and Technology. Next slide, please. All right, so reminders, we have session norms. We are encouraging you to engage actively, immerse yourself in this learning experience. Be open. We are here to have meaningful conversations with each other and ask away. There are no dumb questions. Don't be afraid to ask when you need to. And of course, respect everyone. Let's give each other our undivided attention. So, kumusta po tayong lahat? How are you today? How are you this week? So, are you feeling like number one? You are just happy that you have survived this week, or chill lang ba kayo? Number two, or you are excited? May energy pa ba kayo for this afternoon session? After the whole week, can I get a one, two, or three? So maraming one. Congratulations po that you have survived this week. Sana all sa mga sobrang chill. Keep it up. All right. So next slide, please. Okay, we have few reminders, by the way, for our participants. So we have, next slide, please. Okay, if you haven't joined yet po, kindly visit sea.qcsp.institute to join the Premier Quantum Hackathon in Southeast Asia. Next slide, please. So again, about this hackathon, the registration period is from the 3rd of March until April 18, 2025. So malapit na po yung deadline, so habol po kayo. And if you get selected po, the training and selection will be on May 5 to June 27, 2025. And if you get selected, by the way, your local travel, accommodations, food are sponsored by the organizers in Thailand. So therefore, there is a support for the flight expenses. And we have innovation tracks in healthcare and medicine, climate change, and renewable energy. So hopefully we can have a lot of participants coming from here in our lecture series joining the Southeast Asian Quantathon. Okay, next slide, please. And we also invite you to join us this April 14th, 6 p.m. That would be on that will be on Monday, no? Together with Dr. Ian Jasper Agulo from UP Baguio and yours truly. So if you haven't yet registered yet, you can scan the QR code, and also we will share later the link for you to be able to register sa ating celebrate the World Quantum Day. So see you on Monday about that. So next slide, please. And of course, if you want to communicate with us further, get in touch with us in terms of partnerships, collaborations, school orgs and communities, and many more. So please don't hesitate to reach out to team@qcsp.ph and also jabez.ison at qcsp.ph. Next slide, please. All right, so we are already on session 7. Today is April 12. We are going to have Grover's algorithm, RSA, and ECC. So if you are still with us sa this session 7, no, for being consistent, so palakpakan nyo naman po yung mga sarili nyo for being here with us in this Saturday afternoon. So a round of applause to everyone dahil andito kayo. You are willing to learn something new. Next slide, please. Okay, we have post-program checklist, by the way. Next slide, please. To successfully complete the program, so meaning this whole lecture series that we are doing, here's what you're going to do. Make sure that your attendance is your participation is 70%, and then you have an 80% for the completion of what we require you to do. So homework should be 59.5%, no, for the for all the homework completion. And then post-program survey will be available after the 13th session. So session 7 pa lang naman tayo. So you can still keep up naman. And then at least one entry of the XQBit project, which was actually launched by Jules a weeks ago. So for the XQBit project, next slide, please. So we have, as a part of your offboarding checklist, that you are required to choose and create one of the following XQBit projects. So kindly do a screenshot para hindi nyo po makalimutan. We have content creation, quantum analogy, and lecture recap. So there, next slide, please, because there is a general overview of the XQBit project. So for the content creation, you need to have like, and one of the examples for the general task is it's related to digital or traditional art, poster, or infographics. You can have it solo or with a partner, and your content should represent the key ideas related to quantum computing. For the quantum analogy, we have the general task like skit or animation. It could be solo or by group, but you only have to have a minimum of 2, but a maximum of 5 members. And it's going to be 60 to 90-second video. But the video must use analogies to explain one core quantum computing concept in a simple, creative, and engaging way. And lastly, the lecture recap. The general task is for you to have an explainer video or tutorial video, and it's going to be by group, at least 3 to 5, and at most 5 members. So minimum of 3 minutes and maximum of 5 minutes, and the video must explain quantum concepts that is tackled during the lecture series and must be able to explain it with accuracy. So next slide, please. So kindly do a screenshot or scan the QR code for the XQBit tally form. So remember, we are requiring you to do at least one lang naman for you to be able to also get the certificates from us. All right. So next slide, please. Are you ready for this afternoon session? So let me introduce to you our speaker. Next slide, please. Mr. Jeff Aborot. Mr. Jeff Aborot is a leading figure in quantum computing research and development in the Philippines. He currently serves as the project lead of the Quantum Circuit Simulation Project at the Department of Science and Technology, Advanced Science and Technology Institute, also known as DOST-ASTI. This pioneering initiative aims to provide local researchers with access to quantum circuit simulation software packages through the computing and archiving research environment in high-performing computing facility. And under Mr. Aborot's leadership, this project strives to enable Filipino researchers to design and analyze quantum algorithms for small problem instances, fostering the growth of quantum computing expertise in the country. His work is instrumental in bridging the gap between theoretical quantum concepts and practical applications in the Philippine context. Mr. Aborot is actively involved in promoting quantum computing education and awareness, and he has participated in various conferences and workshops, including the Philippine Computing Society Congress in 2023, where he presented on ASTI's projects and the government's efforts in quantum computing. As a respected voice in the field, Mr. Aborot collaborates with academic institutions and industry partners to advance quantum computing research and development in the Philippines. And his expertise and leadership are helping to position the country at the forefront of this transformative technology. Let's give a virtual round of applause to Mr. Jeff Aborot. Mr. Jeff Aborot, thank you for coming, and you may take the floor.
Thank you, Ms. Steph. Good afternoon. Am I being heard clearly?
Yes po, you are audible, sir. Thank you.
Okay, thank you. Let me share my slide. Okay. Is my screen visible right now?
Yes, sir, but we can see the notes of your screen.
Oh,
Opo.
okay. Sige, let me just adjust.
Yeah, sure po.
Is it still the same?
Still the same po.
Okay. How about now?
I think I can see a blank screen po. Mm-mm.
Wait, how about if I change my so
Probably the screen is extended or
yeah. So let me adjust my screen.
okay po. Sure, take your time po, sir.
Is it better now?
Nothing is showing as of the moment po.
Wait,
Okay.
let me just reply to share.
Okay.
How about now?
That's better po. Yes, it's working.
Okay,
Thank
thank you, Lord.
you.
Thank you. So thank you for the very lengthy introduction. So let me just set my timer. So I think I have around 1 hour and 15 minutes maybe. Okay. Good afternoon. So I think the participants are from the different universities in the Philippines, right? So good afternoon again. I'm Jeff. So I'm just one of the researchers in the Department of Science and Technologies, Advanced Science and Technology Institute. My background is in computer science. So my perspective towards quantum computing is from the computer science point of view. So I'm not a physics person. I won't be able to tell you something about how qubits work in, in the physical setting. But my understanding is more of the algorithms, procedures, computing problems. So, uh, so I'm from the Quantum Innovation Lab. So, Quantum Innovation Lab is a small laboratory in ASTI wherein we um, uh, try to investigate potential applications of quantum computing into relevant, societally relevant problems in the Philippines. So if you are interested in working on applications of quantum computing, uh, you can just send us an email. Okay. So again, good afternoon. I'll be talking about Grover's algorithm this afternoon. So Grover's algorithm for the unsorted list search problem. So for the learning objectives, um, first, we would like you to be able to identify and explain in high level how quantum oracles work. Second would be for you to be able to identify and explain key subroutines and early quantum algorithms. Third would be for you to be able to explain how Grover's algorithm uses these key subroutines in solving the unstructured search problem. So before we uh, go into the details of Weber's algorithm, we'll be going through some background concepts that are needed for us to be able to wrap our head around Weber's algorithm. So I think the majority of the content of this talk will be focusing on these fundamental concepts, and the rest will be on Weber's algorithm. So first, we have the concept of circuit model and circuit complexity. Um, so I think in the past lectures or presentations, the the presenters were able to introduce you to um, quantum circuits. So it is just a model or one of the models of quantum computation. So I think familiar tayo dito kasi in college, we are introduced into the concepts of circuits. So basically um, we have wires and we have gates, right? And so we have the concept of circuit complexity. And since we're talking about complexity, in the circuit model, we would like to define we define the circuit complexity to be the least number of gates. So not necessarily quantum gates, but the least number of operators or gates that is required to implement a specific algorithm. So whether that be classical or quantum algorithm. This is with respect to some universal set of quantum gates used in a specific hardware implementation of the computer. So for example, some computer architectures may be using a different set of gates to implement software programs, while some other computer architectures may be using a different set of gates. So when we say gates, so we're talking about logic gates. And we have this idea of an efficient quantum algorithm to be that which has a polynomial circuit complexity relative to the number of the input bits to the circuit. So when we say polynomial circuit complexity, so we're saying that we want the complexity to be in the range of to be bounded above by a polynomial function. No? So as the size of our input grows, represented here by the lowercase letter n. So as the size of our input grows, we want our circuit complexity to grow in a polynomial fashion. No? Beyond that, medyo ano siya, undesirable kasi ibig sabihin, it takes more computation for our algorithm to complete. So we want na either polynomial or lower. Okay. So here we have a specific example, specific instance of a quantum circuit or a Toffoli gate. So maybe Toffoli gate has already been introduced in the past lectures, but it is just a control gate. So we have here the lower bits to corresponding to the target bits and the topmost bit corresponding to the target bit. So here is a specific decomposition of the Toffoli gate. So here we see that the decomposition uses a single qubit and two qubit gates. Okay. So and there are 16 and 2 qubit quantum gates for this specific decomposition of the Toffoli gate. While in this specific decomposition, we see that we can decompose the Toffoli gate using fewer 1 and 2 qubit quantum gates, but when using a different set of gates. So here we see that it is quite difficult to determine the circuit complexity of a quantum algorithm because it will depend on the specific set of quantum gates that we're using for computation in the physical level. Now, given that it is quite difficult to determine the circuit complexity of the quantum algorithm, the circuit model. There is an alternative complexity uh, metric that we can use to classify our quantum algorithms. And here we have the theory complexity. So before we proceed to the concept of theory complexity, we have the idea of an oracle, which is just a black box function that we can call in our algorithm program to answer a single specific question, and that which returns an output. So without us knowing its inner workings, kaya siya black box, no? I think those with computer science background are very familiar doon sa black boxing approach to designing algorithms. So given that we have an oracle, we can talk about pure complexity, which is just the number of calls made by our algorithm to a black box function F, or the number of queries made to an oracle needed to solve the problem. So instead of counting the number of gates in the circuit, we are now talking about um, how many calls did my algorithm need to the oracle in order to solve the problem. So uh, we assume that we don't care about the specific implementation of the oracle, kasi nga black box siya, and we are just counting the number of calls of the oracle, and we are not counting the other operations in the algorithm. Okay. So an example of a series of queries to an oracle would be, for example, our algorithm would ask the oracle, oracle, does item 1 satisfy property X? Then the oracle would say no. And then next, our algorithm would ask the oracle, does item 2 satisfy property X? And the oracle may say yes. So note that if the oracle will be answering yes or no. We'll be providing yes or no answers to our questions, then you can just encode these as binary values, 0 or 1. Now, for an analogy, I think we are more familiar with the idea of a local program accessing a remote service. So in our local program, we have raw input, and then we encode that raw input into binary values in the low-level computation. And then we do some transformations on the encoding of our raw input. And then we provide that transform value to the oracle, which in this case we treat as a remote service. So the oracle does its job of evaluating the input. So it has this internal function f, and then it outputs a binary value of either a 0 or 1, and then some reversibility function is applied because we know that in quantum computation, the operations are required to be reversible. Okay? And then after that, it outputs a value that is returned back to our calling function. And then this may be performed iteratively after some number of iterations. Our program provides us the output, which hopefully corresponds to the solution to our problem. So in theory complexity, we're just measuring the number of calls to the remote service. So the lesser the number of calls to our remote service, the more efficient our algorithm is. Okay, so given that idea of an oracle, now we define a quantum oracle. So quantum oracle is just a Boolean function which is a binary mapping from binary strings of length n to either a 0 or a 1. And so we can then define the inner workings of an Oracle visible truth table. And in the circuit model, we can implement the operation of the Oracle using logic gates. And as I said, the circuit implementation of an Oracle, quantum Oracle, needs to be reversible. So that means that if we apply the Oracle gate to the state of our qubits by a factor of 2, that means that we will get get the initial state of our qubits. No? Kasi di ba nga, yung inverse ng isang quantum operator, quantum gate is itself. So when we apply it twice, then we just get the identity operator. Okay. So, so here we have a scheme for an Oracle, implementation of an Oracle, given two qubits. So here we have qubit Y as the answer qubit and qubit X as the input qubit. So given the state of the input qubit X, we provide it to the Oracle, or we operate the Oracle into the state of the input qubit X, and then that results to the evaluation of the Oracle corresponding to the evaluation f of X, and then using the XOR gate, we are able to encode the output of the Oracle into the state of our answer qubit Y. So we know that when doing XOR logical operation, for example, if Y is in the state 0, then applying an XOR given Y and f of X, then we will just get the state f of X, or the value f of X. So basically, we are able to encode f of X into the state of our answer qubit. So ito yung very basic scheme for an Oracle in the quantum setting. Meron na pala akong citation dito. So later sa dulo, I'll be flashing yung references ng mga tables, so that you can try to look for those references offline. Okay, so now, given the illustration of local and remote surveys, we see that we can treat the remote surveys as a quantum gate, since that implements the functioning of an Oracle. So kanina, we're looking at it in the classical point of view. There's a usual na calls to remote services. But in this illustration, we can view the remote service as the execution of a quantum gate, or in this case, the execution of a quantum gate corresponding to a quantum Oracle. So again, pure complexity corresponds to the question, how many times do we need to call the remote service to solve our local problem? And the lesser the number of calls to the remote service, the more efficient our algorithm is. So with respect to a specific author, of course. Okay.
Hi, Jeff.
So, yeah.
Parang yung boses mo garbled eh. It has
Oh,
something
okay.
to do with your ano siguro.
Okay.
Device.
I think it's with the electric fan. So let me
Okay.
turn it off.
That's good.
Better.
Sige nga ulit, Jeff.
Hello. Hello. Test mic. Test. Test mic.
Mukhang okay naman.
Okay. Thank you, Sir Bob.
Thank you.
Okay. Yeah. So, so how does the quantum oracle work? Okay. So, given that we have the state of our input qubit X and the state of our answer qubit Y, we
Jeff,
denote, yeah.
sorry, Jeff. Nandyan pa rin eh. Hindi
Okay.
kaya
Let me try to
sa mic siguro.
adjust my mic.
Hello, hello, hello. Test mic, test mic.
Test mic nga ulit.
Better. Test mic. Hello.
Yan,
Test mic.
mas maganda na.
Okay,
Crisp.
okay.
Ah.
Yeah, thank you.
Ah.
Puno na kasi yung USB ports ko. Sige. Okay, so how does a quantum oracle work? Okay, so again, given the state of our input qubit X, so in this case denoted as ket X, and then the state of our answer qubit Y. So in this case denoted by ket Y, we have the quantum gate corresponding to our oracle. So in this case, we denote it as U sub F. So here, diba dito sa illustration, yung oracle natin, we denote it as a single box, U sub F. So ito yung ano nun. Ito yung scope nitong U sub F. Okay, so it includes yung XOR operation. Okay. So again, yung ating answer qubit ket Y encodes the answer of the oracle to the query of a X. So that would be Y. And then the state of this answer qubit transforms into the state Y, X, or F of X after the operation of the oracle operator on the two qubits, or the qubits input and answer qubits. Okay. And then yung ating basis vector X is its state encodes the value of the input X to the oracle. So this would be so for example, if we have one qubit corresponding to our input qubit, then its state ket X would correspond to either a 0 or a 1 or a superposition of 0 and 1. Okay. I think na introduce na rin yung concept ng superposition in the previous lectures. So the state of our input qubit ket X can be either ket 0, ket 1, or a superposition of the states ket 0 and ket 1. Okay. Now to arrive at the answer to the query f of X, we can set the state ket Y into the state 0, since we know that when we do an XOR of a value with a 0, we just get that value. So basically, we're encoding the answer of the oracle dun sa state ng answer qubit. And then we wrap the oracle inside a reversible circuit denoted by the quantum gate U sub F. So yung oracle is yung inner workings ng oracle ay defined within this quantum gate U sub F. Okay. So kung paano yung implementation ng oracle, that will depend on the specific problem that we are trying to solve. Okay, so these three illustrations are three alternative representations of how the quantum oracle works. So this one is using the classical representation ng oracle and the reversible operator. So in this case, we're using XOR. This one, we're using yung quantum gate representation sa circuit model, quantum circuit model. And this one is more of a mathematical expression. So the first qubit corresponds to the input qubit. The second qubit corresponds to the answer qubit. Okay. Okay. So we have a quantum oracle that encodes the answer of the oracle to the state of the answer qubit. We can also implement the oracle using phase kickback effect. Okay, so what does phase kickback mean? No, so this is an alternative implementation of an oracle. So the same pa rin as with the original idea for a quantum oracle, no? Ini-encode pa rin natin doon sa state ng ating answer qubit, get y, yung answer ng oracle. But this time, instead of putting our answer qubit in the state ket 0, so dito, di ba, sa previous slide, ito, di ba, naka ket 0 yung ating answer qubit. So instead of that, we are putting our answer qubit into the state ket negative. So I think the ket negative state has already been introduced also in the previous slide, previous presentation. So I think if Sir Bob presented about the early quantum algorithms like Deutsch-Jozsa algorithm, so the ket minus state is also used in those algorithms. So instead of using the ket 0 state for our answer qubit, we're using the ket minus state. Okay, which is a superposition of the states ket 0 and ket 1, and wherein ket 1 has a negative phase for its amplitude. Okay, and then we operate the oracle quantum gate U sub F on the answer and input qubits. Okay, so ang effect is that instead of encoding the answer of the oracle into the state of our answer qubit, this one, ang effect is that nagkakaroon ng phase change yung composite state, which we can express as this expression -1 raised to f of x. So the answer qubit x acquires a phase of -1 raised to f of x. So if ganoon yung effect, no, ng alternative method na to, and so hindi nababago, no, yung state ng ating answer qubit. And so usually dinidenote lang yung effect ng method na to be this transformation, no. Dinadrop yung ket minus state ng answer qubit kasi yung phase na na-acquire ay ina-attribute doon sa amplitude ng state ng ating input qubit, no. So instead of doon sa answer qubit na encode yung answer ng oracle, in this case doon sa phase ng amplitude ng input qubit na encode yung answer ng oracle. So how does this work? So meron lang two cases. So if we have the output y to be 0, so we know that kapag naging 0 yung f of x, nagiging 1 lang to. So ano lang, retain lang yung original state na ket x, ket minus. But if the output of the oracle is a 1, and so magiging 1 yung f of x dito, so magiging -1 to. And so magkakaroon ng phase flip from positive to negative yung ating answer qubit. Okay. So when f of x is equal to 1. So very basic, no? Very basic na idea na sa ngayon parang wala siyang gamit, but itong phase kickback is one of the key subroutines na ginagamit sa mga quantum algorithms, including Gruber's algorithm, I think Shor's algorithm. So yung phase kickback is a part of the toolbox of quantum algorithm designers, okay, when developing new quantum algorithms. Okay. Okay, so just a step-by-step run through of the evaluation of the application of the quantum gate U sub f into the initial state ket x and ket minus. So here we just blow up yung ket minus, and then we apply yung quantum gate U sub f to the superposition of states. So here we see that with the help of the superposition effect, we can evaluate or operate a quantum oracle into the superposition of states 0 and 1. So here we can evaluate for the case na 0 yung ating answer qubit, and 1 yung ating answer qubit. Okay. And then yung evaluation ng x on the oracle ay may encode doon sa state ng ating answer qubit. And if f of x is 0, then it follows na walang change doon sa initial state natin. So walang phase change sa amplitude ng ating answer qubit or input qubit. But if f of x is 1, then tracing the evaluation, we see that mababaligtad, no? Mababaligtad ngayon yung phase ng ating superposition states ket 0 and ket 1. So magiging negative yung phase ng amplitude ng ket 0 at magiging positive yung phase ng amplitude ng ket 1. But that is just ano no, the same as the negative, as the ket minus with the negative amplitude or negative phase of its amplitude. No? So ngayon itong negative phase na to, we can attribute it to the change in phase of the amplitude of our input qubits state. Okay. So ganun. So ito, ano lang siya, no, basic case lang. We just assume that meron lang tayong isang qubit for our input qubit x. So either 0 or 1 lang yung ating input qubit x, but we can also use this trace of the operation of the quantum oracle into the state of our input and answer qubits, even when we have multiple qubits corresponding to our input qubits. Okay, so that's the first alternative for the phase quantum oracle. We also have a second alternative for implementing the phase quantum oracle. So for this alternative approach, we instead of using yung ano no, yung quantum gate for our oracle, and using yung ket minus na state for our answer qubit. So here we are using yung ket y state to be in state ket 0, and then so ganito parang yung original encoding, no, ganito siya yung kalalabasan ng application ng quantum oracle, ket x and ket f of x, and then we operate a z gate on the answer qubit. So we know na yung z gate, ang effect niya sa ket 0 na state would just be the ket 0 state, but ang effect niya sa ket 1 na state would be yung negative ket 1 na state. So nagkakaroon ng flipping ng phase kapag 1 yung input na quantum state sa z gate. Okay? So when we do that, similar yung effect, no? Na kasi kapag 0 ito, then that would just be the same, no? Magiging ket x, ket f of x. But if 1 yung f of x, then magiging negative 1 to. So magkakaroon ng phase flip doon sa amplitude ng state ket x. After doing that, we operate the oracle quantum gate u sub f on the answer input qubit. So dalawang beses yung operation ng oracle quantum gate u sub f doon sa input and answer qubits. The reason for that is that we want na yung kalalabasan na final state ay the same, no? The same noong ating initial state, which is ket x, ket 0. But this time meron na tayo noong change up, encoding noong answer ng oracle in the form of a conditional phase flip, okay? Negative 1 to the f of x. So the same yung effect, but we use two operations of the quantum oracle gate, and we use a z gate, no, to encode yung f of x doon sa amplitude. Okay. Kasi dito sa step 3 or sa first step, wala pa namang potential or conditional phase flip, wala pa naman. So noon lang in-apply natin yung Z gate doon sa ating cat x, cat f of x state, tsaka lang na-encode yung conditional phase flip doon sa amplitude ng ating input and answer qubits. Okay, so again, we need to call on the oracle twice, and we need to use an extra gate, which is yung Z gate. Okay, so ito yung alternative 2. Okay, so given the description of the quantum oracle and the phase quantum oracle and the Boolean oracle, so here are some potential implementations of an oracle in Boolean and phase case. So, for example, yung idea ng mark dito is that we mark a specific quantum state in a superposition of many quantum states by changing its phase. So, for example, if we have 2 qubits, and then we put it into a superposition. So superposition yun ng states na 0, 0, 0, 1, 1, 0, 1, 1, and then may amplitude na 1/2, no? Bawat superposition state. And so let's say we want to mark yung state na 0, 1. So yung state na 0, 1, kasi diba initially positive yung kanilang mga amplitude, i-phase ang kanilang mga amplitudes, if we will be starting from the initial state na 0, 0, then we apply a Hadamard operator, no, doon sa initial state, then we will get a ket plus na superposition state. And so if we want to mark a specific quantum state doon sa superposition, let's say state 0, 1, then gusto natin na yung state na 0, 1 yung magkakaroon ng phase flip sa kanyang amplitude, no? So magiging plus 0, 0 minus ket 0, 1 plus ket 1, 0 plus ket 1, 1. Okay, so an oracle is able to effectively mark a specific state in a superposition if we encode, no, yung state na target natin into these specific constructions. So for example, in the Boolean oracle, if we want to mark yung state na 0, 0, 0, in the case na tatlo yung qubits, tatlo yung ating qubits corresponding to the input qubits, then so assuming na ang starting state ng mga qubits ay 0, 0, 0, and so we want to trigger yung flip sa phase by using a multi-qubit controlled NOT operator. And so for us to be able to trigger itong ating controlled 3-qubit controlled NOT, then we first flip yung states ng ating input qubits kasi nga 0, 0, 0 yung initial state, so para maging 1, 1, 1, and then matitrigger itong itong state ng ating ancilla qubit, which is yung magte-trigger ng flip sa phase, and then we flip back yung state ng ating input qubits using again set of X gates. Okay, so sa case naman na yung gusto nating i-mark na state is 0, 0, 1, then we just need to flip yung Q sub 1 and Q sub 2 na qubits. So para maging 1, 1 pagdating dito, no? 1, 1 yung state nung 111 yung magiging state ng qubits, and then yun yung magte-trigger ng phase flip na operation. Okay. So yun yung sa case ng Boolean oracle. Sa case naman ng phase oracle, instead of using an ancilla qubit, we're not using an ancilla qubit dito sa phase oracle na approach. This one, no, using yung Z-gate. So we know na kasi yung Z-gate is able to effectively mark a specific state, kasi may effect lang siya kapag one yung input na quantum state sa kanya. So sa phase oracle version, we do not need an ancilla qubit to encode the phase flip effect or phase kickback effect. Okay. So later dun sa last slide, included din yung paper na ito, TCAT 2017. So I think their paper is about specific implementation of oracles for the 3-qubit scenario for the Grover's algorithm. So it's an interesting paper to read. Okay. Kasi doon pinapakita kung paano ba i-implement yung quantum oracle if you will be writing it into a software program that is intended to run on a quantum processor. Okay. Okay, so given the background concepts of circuit complexity, Fourier complexity, Boolean oracles, quantum oracles, phase quantum oracles, and the alternative methods of implementing the phase quantum oracles into quantum circuits, and the possible construction of the inner workings of a quantum oracle into a quantum circuit, given that you know which specific quantum state you would like to target or to mark. Also given the background concepts on quantum superposition and the basic quantum gates na Hadamard gate, X gate, Z gate, we can now proceed with presentation of Grover's algorithm. So yung problem na ginagawa ng Grover's algorithm is yung problem searching for an item in an unsorted list. Okay, so the givens are an unsorted list of items, an oracle, which is just a black box function f that maps n qubit inputs into 1 qubit outputs. Okay, so ito yung mapping, no, ng function f from n bit strings to one bit or 1 qubit in it's a case ng quantum setting. And then for specific x in the set of all possible n-bit strings, there is a specific item which we denote as a good item, wherein yung evaluation ng f on x is equal to 1. So ito yung item na gusto nating mahanap doon sa unsorted list of items. Okay. So the problem statement would be find x such that x is a good item. So given an unsorted list, find x such that x is a good item, or find x such that f of x is equal to 1. And our assumption would be that there exists one good item in the unsorted list. So of course, there are cases wherein there are more than one good items in the unsorted list, but for this presentation, we'll be focusing on doon sa case na one good item lang yung meron doon sa unsorted list. And if so if there are 2 to the n possible n-bit strings doon sa domain ng possible inputs, then and there is one good item in the unsorted list, then there are 2 to the n minus 1 bad items. Okay. Yeah, so very basic lang naman itong ano no, definition itong unsorted list search problem. And yung mga algorithms like like Grover's algorithm, they're not really parang designed to show yung ano ba, yung separability between classical and quantum computation. But ang intention is that when Grover's algorithm was discovered by Love Grover, maka-identify ng problem wherein there is a clear separation between efficiency of classical and quantum algorithms, so that it is interesting to study quantum algorithms. So I think ganun sa case ng Deutsch and Deutsch sa algorithm, very basic lang, di ba, yung problem? We just like to know if a function if is balanced or constant. So very trivial, no? Parang contrive yung problem. But the intention is not for it to be applicable, but just to discover problems wherein there is a clear separation between the efficiency of algorithms in the classical and quantum setting. And so that leads to interest in studying quantum algorithms para makadiscover pa ng other most likely more applicable na advantage ng quantum computers over classical computers. Okay, so Grover's algorithm is one such algorithm. So here is a very naive classical algorithm for solving the unsorted list search problem. So in the best case, so for example, we have these unsorted list of items, and then we want to find a single good item from the unsorted list. So what we can try is to just pick items in the list, no? And so we can be so lucky such that yung first item na mapick natin is yung good item. So in that case, meron lang tayong one try and then nahanap na natin yung good item doon sa unsorted list. So that's the best case. The worst case would be yung last item na pipick natin is yung good item. So in that case, we will need 2 to the n tries, no, before natin mahanap yung good item. In average, we will need to pick an item in the unsorted list in this amount of tries. So before we find the good item to the unsorted list. So here is just a calculation of the average number of tries that we need to make if we will approach the solution, if we will approach the problem by picking items in the list. We will need this much number of tries, 2 to the n plus 1 over 2, which is in O of 2 to the n na query complexity. Okay. So parang ano siya, imagine we have this unsorted list and then magpipick tayo from the 2 to the n na items. Tapos tatanungin natin sa Oracle, is this a good item that I am looking for? Tapos sasabihin ni Oracle, either yes or no. Okay. So since we are asking the Oracle about each item, then we are talking about query complexity. Okay. So again, itong classical algorithm will require us number of tries in O2 to the n, which is not, well, in average, no, parang hahatiin mo. So parang hatiin mo yung list. You can do sorting muna dun sa list siguro if you can order the items that you need to account for that sorting pre-processing step, of course. Now, sa quantum setting, we have Grover's algorithm, no? So basically, yung Grover's algorithm sits on top of the phase kickback effect na pinursan ko kanina. So the idea is that so there are two main concepts na kung saan nag-rely yung Grover's algorithm. Three. Okay. So first would be superposition of quantum states. Why? Because if we are trying to query the oracle, di ba we want na gusto nating matanong yung oracle on all possible items, on all items in the unsorted list once lang, di ba? So we don't want na kagaya sa classical na tatanungin natin yung oracle parang paisa-isa. But sa quantum setting, meron tayong advantage through the superposition, idea ng superposition, wherein we can ask the oracle on all possible, on all items doon sa list, no? So we put these items into a superposition and then we query the oracle. Then the oracle provides us again also with a superposition, no? So ngayon, that's first, superposition. Second is yung phase kickback effect. So how does it helps doon sa Grover's algorithm? So di ba yung general idea ng phase kickback would be to mark a specific state in a superposition, no? Of course, yung behavior ng oracle depends on our purpose, no? Which means specific siya dun sa problem that we're solving. But in general, yung behavior ng phase kickback is that namamark niya yung specific state wherein yung evaluation ng oracle resolves to A1, meaning f of x is equal to 1. Okay? Kasi yung naging effect nun is that yung phase ng amplitude ng state na yon ay nafi-flip. So meaning nafi-flip, meaning from a positive na phase, nafi-flip into a negative na phase, and if negative yung phase, nafi-flip into a positive na phase. So sa kanya lang, doon lang sa specific state na yon, nangyayari yung ganong phase flip. Sa other states, no, sa superposition, since ang evaluation ng oracle would be 0 or f of x is equal to 0, yung amplitude ay nare-retain, no, doon sa original niya na phase, no? So kung positive siya, then positive lang. Kung negative siya, then negative lang. Okay. So ngayon, yung contribution ng phase kickback effect is that si oracle, pag binigyan natin siya ng superposition of all the items in the unsorted list, the oracle is able to mark this specific item that we are looking for, or yung good item na tinatawag natin. And then for the rest of the items na bad items, na-retain lang yung phase, no, ng kanilang amplitude. Okay. So basically yung oracle marks yung state na kung saan interested tayo. Okay. So yun yung contribution ng phase kickback. Another subroutine is yung amplitude amplification, which hindi ko na na-include dito dahil sa time. Yung idea ng amplitude amplification is that may mga specific lang na states doon sa superposition wherein we amplify yung amplitude nitong state na to. We amplify. And then we decrease yung yung amplitude ng other state. So in combination with phase kickback effect, we can target yung mark state. We can target yung amplitude ng mark state to amplify it. So ma-amplify yung amplitude ng mark state. But yung amplitude ng bad states ay madi-decrease. So ano ba yung purpose ng subroutine na pag-amplify ng states or amplify ng amplitudes? So yung purpose nun is that as we know, di ba, in quantum computation, hindi siya kagaya ng classical computation na definite na yung nakukuha mong sagot. Sa quantum computation, di ba, naka-superposition yung states. And so if we want to get an output from our computation, we need to do a physical measurement doon sa state ng ating qubits. So meron tayong superposition. When we measure the state of our qubits, then isa doon sa mga superposition na state yung nakukuha natin. Okay? So parang sa coin, di ba? When we flip, we get either a 0 or a 1. So siguro we can look at the process of tossing a coin as a measurement operation wherein we get either a head or a tail. But we know doon sa coin, parehong 50-50 yung amplitude ng ating head and tail. But what if we can amplify yung amplitude either ng head or ng tail such that pag nag-toss tayo ng coin, most of the time ang lalabas ay yung head, or yung tail. So yun yung effect or yun yung help na kino-contribute ng amplitude amplification sa Grover's algorithm. Pinapalaki niya yung amplitude ng mark state, then pinapaliit niya yung amplitude ng bad states. Okay? So that when we do a measurement doon sa state ng ating input qubits, ang makukuha natin with very high probability ay yung state na mark ng oracle, which corresponds to the solution to our problem. So yun yung three fundamental subroutines na ginagamit sa Grover's algorithm. Superposition, phase kickback through phase quantum oracle, and yung amplitude amplification na subroutine. Okay, so daanan natin yung Grover's algorithm. So ang idea is that kagaya lang din doon sa phase kickback subroutine, phase kickback using phase quantum oracle, we have our answer qubit and our input qubits. So we have a single qubit for our answer qubit, and we have n qubits for input qubits. Okay. So kasi 'di ba nga yung oracle is a mapping between n bits to a single bit. Okay. And then we put our answer qubit into the ket minus state. Okay. So 'di ba para ma-put natin into the ket minus state yung isang qubit na nasa ket 0 state, we need to first na apply yung X operator doon sa ket 0 state para maging ket 1, and then we apply yung H operator doon sa ket 1 para maging ket minus state. Okay. And then we put yung ating input qubits into a superposition of all the 2 to the n qubit binary strings. Okay? So we use yung Hadamard operator. So for each qubit, we apply yung Hadamard operator. Okay. And then, for a very specific number of iterations, which is the floor of pi over 4 square root of 2 to the n. This is 2 to the n. We apply a series of quantum operations. So first, we apply the phase quantum oracle operation doon sa ating input and answer qubit states. Okay. And then, second, we apply yung diffusion operator. Ito yung, dito pumapasok ngayon yung amplitude amplification na step. And then, after this number of iterations, we measure the state of the input qubits into classical bits, C sub 1 to C sub n. And then, of course, no, since ano nga siya, may probabilistic siya, no? We are not sure, we are not exactly sure if yung makukuha natin na classical binary string will correspond to the good item, no? Until we measure yung state ng ating input qubits. So here, meron tayong test na or evaluation na step wherein we verify if yung resulting classical values correspond to this requirement. Okay. So if yes, no, if f of x, or in this case, no, f of c is equal to 1, then x is the good item that we are looking for. Else, we need to repeat the execution of the Grover's algorithm starting from step 1. Okay. So, unlike doon sa classical na na even yung naive na classical algorithm, di ba, doon sa classical we don't need to repeat, there's no need to repeat the execution of the algorithm. But in Grover's algorithm, there is a chance that we will need to repeat its execution if we are not able to get the good item that we're looking for. So comparing with the classical, with the naive classical algorithm for the unsorted list search problem, si Grover's algorithm, ang complexity niya is this much. Kasi andito yung oracle operator, di ba? Sa 4.1. So the number of times that we need to ask the oracle is this much, no? Floor of pi over 4 square root of 2 to the n. Okay. So later may I think may isang slide yata na lang, very high level explanation kung bakit pi over 4 square root of 2 to the n, no? Bakit yung magic number na yan. So which is in O of square root of 2 to the n, which is a quadratic speed up over the classical complexity of O of 2 to the n. Quadratic meaning if you square this value, we'll just get itong classical query complexity. Okay. So kung meron kang, let's say 100 items doon sa unsorted list, then we will need to query the oracle square root of 100. Okay. So medyo hindi siya ganoon ka-impressive kung maliit lang yung list mo. But imagine if you have millions, billions, trillions of items in your list, then mas nagiging significant yung quadratic speed up over the classical naive algorithm. Okay. So here is yung is a very high-level schema of Grover's algorithm. So ito yung pag-put natin into superposition ng input qubit states at input qubit states, and then pag-call natin sa oracle using the quantum gate U sub f, and then yung amplitude amplification step. Okay. So itong reference na to has a good exposition ng Grover's algorithm. So meron siyang step-by-step na exposition that you can follow. So geometrically, no, we can interpret yung working ng or how Grover's algorithm work using this illustration. So imagine that we have the state, no, yung state ng good item that we are looking for. Let's say we denote it as ket alpha. Okay. And then since doon sa problem statement, 'di ba, isa lang naman yung item, then that we are looking for, then the other items will be bad items. So let's denote yung state ng ating bad items as yung ket alpha perpendicular. So this one. So when we initialize yung ating input and answer qubits into a superposition state, so we are in an initial state ket phi. Okay, so and that is theta angle away from the bad item state ket alpha perpendicular. Okay, some theta angle away, no? So let's say these are vectors. Okay, so ang goal is from our initial state ket phi, we want it to be near ket alpha na state, which is yung target state natin. Okay, so so how do we do that? So, or how does Grover's algorithm do that? Okay, so from here, from the ket phi state, na initial state, Grover's algorithm applies yung Oracle query. Okay, Oracle query. And then, diba doon sa Oracle, sa query to the Oracle, nagkakaroon ng phase kickback. So nagkakaroon ng flipping ng phase. And that is equivalent to what do you call this? Mirroring, no? Yung ket phi about the ket alpha perpendicular na state. So nagiging ano siya. So nami-mirror siya dito sa state na to, about this state. So ito yung resulting na state. In-applyan natin ng phase quantum oracle gate yung ating initial state. So in this case, yung u sub f I denoted as the V operator. Okay, so that's the first step. And then we want to amplify now the amplitude of the mark state. Okay, and so ang nangyayari when we do that is that nami-mirror naman about the initial state ket phi yung ating state na V ket phi. So from here, na-i-mirror sa state na ito, which is yung resulting state na WV ket phi. Okay, so which is now 3 theta away from the undesired bad item state na ket alpha perpendicular. Okay, so this is one iteration nitong subroutine na ito, subroutine number 4, which is yung application ng Oracle operator and application ng amplitude amplification operator. So this is one iteration. So if we want to be near the desired state corresponding to the good item, then we should perform itong mirroring operations several times. And doon ngayon pumapasok yung floor of pi over 4 square root of 2 to the n na number of iterations. So given that number of iterations, it will move the state of the input qubits from this initial state to near this desired state ket alpha. Okay, so bakit pi over 4 square root of 2 to the n? Okay, so let's see. Okay, so here is a very sketch sketch the proof ng ano no, derivation ng pi over 4 squared root 2 to the n. So yung angle alpha ay so we assume some value doon sa for the angle alpha, and then t times 2 theta pala, theta plus t times 2 theta. So we set that to pi over 2, and then assuming that n is large enough, no, we can compute for the value of t, which is the number of iterations na kailangang i-apply yung Oracle and amplitude amplification operator to be pi over 4 square root of 2 to the n. So kapag sumusobra tayo dito sa value na ito, lumalampas tayo doon sa desired state, no? So dito meron yung perpendicular nung ket phi, perpendicular nung initial state ket phi. So kapag lumalampas tayo dito dahil lang sumobra tayo sa number of iterations, nami-miss natin yung optimal amplitude for the desired state ket alpha. So meaning bumababa ulit yung amplitude noong desired state natin. And so ano siya, para siyang, I think yung common analogy na ginagamit sa other references is that para kang nagbe-bake. So meron lang optimal na number of minutes where you need to bake your cake sa oven. Beyond that, nasusunog siya. So undesired state yun. And so yung desired state ay yung optimal distance noong resulting state ay pinakamaliit from the desired state when we iterate yung subroutine number 4 by the floor of pi over 4 squared root of n number of times. Okay. So beyond that, talampas na tayo. Dito na siya. So hindi na siya optimal. So pwede na tayong, so dahil nga ano no, tumataas yung amplitude. So lumalapit sa 100% yung chance na pag nag-measure tayo ng state ng input qubits natin, ang makukuha natin is yung desired state. Okay. So you can go through doon sa derivation nito once I provide yung materials offline. Okay. So this is just the high-level schema for the quantum circuit ng Grover's algorithm. So Grover's algorithm is optimal, no? Wala nang mas bababa pa na number of queries sa Oracle to solve yung unsorted list search problem. And so yung quantum computer cannot go beyond pa doon sa O squared root of 2 to the n, meaning mas mababa pa na number of queries of the Oracle. So the implication is that if a classical computer solves a difficult problem in NP, in exponential number of queries, then yung quantum computer, exponential pa rin, pero mas maliit lang kasi nga ini-square root natin when using Grover's algorithm. And so NP problems cannot be solved more efficiently by checking all possible answers in superposition. So parang magic bullet kasi yung superposition. Parang sabihin na lang natin na parang, edi i-put na lang natin into superposition all the candidate solutions to our problem. And then, mabilis na natin na makukuha yung sagot. But again, bounded nga tayo nitong this much number of calls to the Oracle, no? Ito na yung best na kayang magawa sa unsorted list search problem when using an Oracle for computation. And so we need to look deeper into the other structures of the problem besides the fact that potential solutions can be verified easily. Okay. So we fully rely on the superposition effect to solve our difficult computing problems more efficiently when using quantum resources, okay, or qubits and quantum algorithms. So we need to have a deeper understanding of the inner um, characteristics of our problem, and to take advantage of these characteristics sa perspective ng quantum computing. So in summary, we identify and explain in high level how quantum oracles work, Boolean oracles, quantum oracles, phase quantum oracles, and then we identified key subroutines in these early quantum algorithms. So superpositional state, phase kickback, in the case ng phase quantum oracles, and amplitude amplification, or yung rotation about the state. And then we went about explaining how Grover's algorithm uses quantum oracle, particularly phase quantum oracle, in solving the unstructured or unsorted list search problem. So here are some references that you might want to look into. So ito yung paper nila Figat 2017. So they look into the problem na unsorted list search using Grover's search algorithm sa case na 3 qubits. I think this was done sa IBM quantum computer. 2017 pa, so early version po to ng IBM's quantum processor. And then yung original na paper ni Grover on Grover's algorithm is this one. So hindi talaga siya titled as Grover's algorithm, no? But yung title niya is A Fast Quantum Mechanical Algorithm for Database Search by Love Grover noong 1996. 1996 pa. Yun. And then, so I think hindi ko yata na-include pala yung page on references, but include na lang doon sa material na i-provide ko offline. So if you want to reach me, so you can send me an email. Here is my ASCII email, and the email address of our lab is qil@asci.usc.gov.ph. So I think that ends my presentation on Grover's algorithm for the unsorted list search problem. So I think nag-extend ako yata ng some minutes. Yon. Thank you.
All right. Thank you so much, Sir Jeffrey, for your presentation. And I guess now we are going to proceed with the Q&A na po. So guys, participants, if you have questions, kindly unmute your mic, or you can type your questions in the chat box po. So we have a first question by Kyle. Okay, Sir Jeff, is the graphical representation of the algorithm an approximation of the Hilbert space?
Sorry. Wait. I think. Is Kyle referring to this one? This is just a generic na state space. But I think yes, we can look at it like that, no? Hilbert space, kasi nga yung state, yung mga quantum states, no? They live in Hilbert space, and so yung mga states natin ay always some distance away from each other. So when we are applying operations on quantum states, then we are moving our quantum states in the Hilbert space. So ito, I think this is just a very sketch illustration, kasi lang siya, 2D lang siya. But in reality, di ba, multidimensional yung Hilbert space natin, depending on the number of qubits that we are working on sa quantum computation. So I hope I answered Carl's question.
Yes, thank you for the question. Okay, thank you daw po, sir. Right? Do we have any other questions from the audience po?
Siguro i-add ko lang, no, regarding applicability ng Grover's algorithm. So, kasi before, parang iniisip ng mga researchers na parang Grover's algorithm is just is an algorithm for a toy problem. And so wala siya talagang application. But recently, there are some publications on the application of Grover's algorithm for image processing using quantum computers. So I think particularly doon sa edge detection sa images, so nagagamit siya. Haven't really read yung paper, but it's good to know na may practical application yung Grover's algorithm in real life.
And another follow-up question from Kyle pa rin po. Can we create a general oracle that takes an input of what we want to target?
So yun nga, kasi 'di ba ang catch, no, sa Oracle is that we need to have an idea about the good item so that we can encode it into a circuit. So as of now, I'm negative on the idea of a generic quantum oracle. Para siyang universal oracle ba yun? Yung idea. But yeah, for now, I'm negative on that. But if there is a way to, I don't know, approach it na parang meta description, no, ng good item, so that you can come up with a universal oracle, then I think that would be possible. So it means hindi explicitly yung description ng good item yung i-encode mo sa circuit ng Oracle, but mas kumbaga on a meta level, merong generic characteristics yung good item na hinahanap mo, and with good items other computing problems, no? So maybe if you can extract itong characteristic na to, yun yung i-encode mo doon sa quantum oracle, then the quantum oracle will be able to answer queries for these specific instances of the problem. So for example, kasi diba sa computer science, we are working on generalization of computing problems, wherein these generalizations have specific instances. So for example, the traveling salesman problem, it's an abstraction of specific instances of problems na nag-share ng characteristic ng TSP. So if we can come up with a quantum oracle for the abstract problem of TSP, then yung specific instances noong TSP can also be applied with itong quantum oracle na ma-define for the abstract problem of TSP. So siguro kung ganun titignan yung idea ng generalization, then we can come up with a quantum oracle that can address itong specific instances ng mga problems corresponding to TSP or other abstract problems.
Nice. Thank you very much po, sabi ni Kyle. All right. So do we have any more questions? If you guys want to reach out, no, Sir Jeff Aborot, no, I think he flashed kanina sa screen and how you can contact him po. All right. So do we have any more? Sino pang hahabol na mag-ask ng question?
Oh, sorry. So here. Yeah, here's my email address.
Yes.
Yeah, so if you have questions, you can send me emails and then we can chat. You can chat Zoom or email or Messenger.
All right.
If you want also to visit me, nasa Astin lang ako, we are in UP Diliman campus.
Nice. All right. So at this juncture, again, we would like to thank Sir Jeffrey Abut for his presentation this afternoon. A virtual round of applause, please naman po kay Sir Jeffrey. And
Thank you.
okay, thank you so much. So allow me to share my screen. Right. So
Salamat.
energy, okay. I think energy check naman po tayo bago tayo mag-icebreaker. Maraming salamat, sir. So guys, how
Thank you
are you
po.
feeling? Thank you so much, Sir Jeff. So, ikaw ba si number 1, si number 2, or number 3? Can we get a reply? Oh, number 2. Interesting. Thank you so much. Napaka-interesting naman talaga po yung discussion ni Sir Jeff. 1 and 2. All right. So let's move on to the Kahoot icebreaker. So before we proceed, I would like to announce again, to invite you to the hackathon. So the participants of good standing, sila po yung qualified na maka-join sa hackathon. So we have Ateneo de Daga this June 19, DLSU May 30, and MSU IIT June 5. So QCSP will also be reaching out to you naman po on how you can join this hackathon. All right. Sana makabuo na po kayo ng team ninyo. And then let me share my screen. Okay, so we are waiting for players. So let's join the Kahoot po. You can scan the QR code or type in the PIN. 2365688. Okay, we have Anthony. Dalawa pa lang. Okay, let's wait for the others. I think you can use your phone. Yes. Ayan. Right. I think let's wait for a couple of seconds more. Ayan. Ready na ba ang lahat? May habol pa ba? Let's start. Okay. I think 1 minute more kasi may humahabol pa eh. Let's start at 5:53. Yes. Okay, I think okay na yan. So let's start. Are you ready? Okay. So what does quantum circuit represent? Yan. The answer is quantum operations. Ooh. C. M. Pakaon. Number 1. All right. Next question. What is the main goal of Deutsch-Josa algorithm? Thank you, Sir Jeffrey. Ingat po kayo. So the answer is to determine if a function is constant or balanced. Let's see. Sinong nasa leaderboard? Justin Gonzalez. Next. What is the main goal of the Bernstein-Vazirani algorithm? Okay. Just. Okay, find the hidden number. For the leaderboard, we have still Justin is ranking number 1. True or false? Quantum circuits can be simulated classically. All right, so the answer is false. Justin pa rin yung number 1. Ang bilis niya mag-answer ah. Next. What is the key feature of quantum algorithm? Okay, it is superposition. Tignan natin. 4626 na yung score ni Justin. Ang galing. Which of this is a quantum gate? Okay, the answer is Hadamard gate. Next. Uy, si Justin pa rin talaga yung number 1. Ang galing-galing mo, Mr. Gonzalez. What is the common application of quantum circuits? The answer is cryptography. Sana nakuha niyo yun lahat kasi yun talaga yung common answer. We have Justin pa rin yung number 1. Yes?
Pinakita kanina yung pin eh.
Po?
Andyan yung pin, game pin, 2365688 yung sa baba.
Okay.
Ah.
Ooh, the game pin.
2365688.
Okay. So, the answer is decoherence. So, Sir Bob, yung pin po is
2365688.
5688. Okay. Thank you so much. Next is... Okay. Si Justin pa rin talaga yung number 1. 9 of 12 na tayo. What is the role of a quantum gate? Okay. Manipulate qubits yung tamang sagot. Ay, sorry. Sorry na. Next ko na. Okay, which of these is a quantum algorithm? Sige, let's just check the scores later. Okay, the answer is Grover's algorithm. Kakadiscuss lang yan ni Sir Jeff kanina. Justin Gonzalez, number 1. What is the significance of quantum entanglement? Okay, instantaneous state correlation. Si Justin pa rin talaga ang pinakamalakas. And the last question is, what does VQP stand for? All right, the answer is bounded error quantum polynomial time. And the winners are, we have Ren, we have Justin, number 2, my bagong winner. We have Pauline. Congratulations, everyone. Uy, nakahabol si Pauline. Ang galing. We have runners-up, Jerome, and hindi ko nakita yung isa. Thank you so much for your participation. At this juncture, we are going to have a 5-minute break, I guess, before the next, next session with Sir Bob. All right. So, let's have a short break po. And see you in a few minutes. Hello, everyone. We are back after our 5-minute break. Let us please welcome the President of Quantum Computing Society of the Philippines, or QCSP, Mr. Bobby Corpus Jr., to present to us or share to us about RSA and ECC. Sir Bob, you may take the floor.
Salamat. Okay, so I hope that okay pa kayo, because that was quite heavy yung sa Grover's algorithm, and this one is also medyo heavy din siya, I mean mathematically, pero mga basic lang naman yung mathematics na ginagamit dito. Let's start with what RSA is. Okay naman ako, narinig naman ako.
Yes, sir. You are audible po. Loud and clear.
Okay. Yeah. So let's start with how to encrypt an RSA. So the motivation for this learning what RSA is and what elliptic curve is because ito kasi yung ginagamit natin, no? Sa lahat ng transaction natin, no? Sa internet, whenever you buy something Amazon, no? It's either RSA or elliptic curve yung ginagamit mo, no? So even sa blockchain, no? Ginagamit sa Bitcoin, no? Whatever kind of cryptocurrency ginagamit is elliptic curve, no? So ang problem lang kasi is these are actually RSA and elliptic curve. They are very anong tawag dyan, elegant piece of mathematics, no? And ano sila, no? It's kumbaga invertible. Pag meron kang key, na-invert mo yung process, no? Kaya yung key na ginagamit mo to encrypt should be private. The key na ginagamit mo to decrypt should be private, no? Yeah. So itong RSA and elliptic curve, these are algorithms in the public key infrastructure cryptography. May dalawa kasing klaseng cryptography. Yung isa is symmetric cryptography at yung isa naman is asymmetric, no, or the public key infrastructure, no, public key cryptography. Ginagamit natin yung symmetric because mabilis siyang mabilis siya pag encryption because of performance, kaya natin siya ginagamit. Ang problem lang is how do I give you the key? No? Yan ang problem. And that's what is being solved by the RSA elliptic curve. No? Tapos, yung yun nga, this is a very elegant piece of mathematics. Unfortunately, the Shor's algorithm can decrypt them. No? So given sufficient number of logical qubits, you can ma-decrypt yung itong na to, algorithms. No? So they are considered broken, no? Sa quantum, in the age of quantum. No? Kaya meron tayong tinatawag na years to quantum. No? This is the number of years bago ma-break yung encryption na yan. No? And there is a prediction na by 2039, 2040, a 2048-bit 2048-bit encryption of RSA will be broken. So kaya that's why we study this. So pag-usapan natin yung how to encrypt, practical muna tayo, and then we are going to explain bakit siya gumagana. Importante siya kasi when we know how it works, we will understand why Shor's algorithm is able to crack that. Okay, so let us start with encryption. So ganito yung problem, no? That is being solved, no? Meron tayong, so Alice and Bob, these are the two characters in the cryptography world, no? Sila yung nag-exchange information, tapos they want to encrypt, no? They want to communicate privately using encryption. Tapos gagamit sila ng isang encryption key. Encryption key na yan, kailangan makuha. So they will have to agree, no? Or let us say gagawa si Alice, and then Alice will have to give this key to Bob. Now, kapag they can meet with each other, then that's good, no? As long as hindi ba intercept, that's secure, no? So physically meet with each other. Pero if it's not possible for them to meet with each other, then they have to send this via the internet. Problem lang is how would they send this, no? Are they going to define another private key to encrypt that and send it to the other party? So ganon din, how do you send that new key to the other party, no? Kaya that's the reason why we need to be able to encrypt the symmetric key and send it via the internet where everyone can see. Pero pag nakita nila, it's encrypted at only the other person can decrypt, no? So may another character dito, si Eve, no? Si Eve is the one that is the eavesdropping, no? Nakikinig siya. She's the one capturing all the packets, no? Now, nung hindi pa uso yung PKI, then you can just dump the packets, no, and be able to see the plain text. So makikita mo yung mga passwords doon. Specifically, makikita mo yung secret key na na sinesend nila. No? Okay. That's the motivation. Okay. So this is where RSA is used. No? The concept of RSA. So RSA pala stands for Rivest, Shamir, and Adelman. No? They are the people who created this encryption algorithm. And merong ang RSA company. So meron tayong dalawang prime number. No? So this one is based on the factoring a number, a composite number, a very large composite number is so hard to do. No? So meron kang dalawang prime numbers, P and Q. When you multiply them, it will give you a composite number, letter N. No? Pagkatapos, so tapos we will need another number E. No? Itong E, this is the one which we will use to encrypt the message. So yung E at yung N, yung pair na yan, they are the public key. So ano yan, no? Pwede mong ilagay yan sa open to the public, no? You can publish it in a well-known URL, no? Or publish it to a PKI server para anyone who wants to message you, they can just get the public key and then encrypt the message. So pag na-encrypt na yung message, even you who encrypted it will not be able to decrypt it. And anyone else will not be able to decrypt it unless they have a private key, which Bob will make sure no one is going to get. No? Okay. So how do we encrypt in RSA? No? So ang una natin gagawin is meron tayong mga letters, no? So kasi mga letters natin, these are internally, these are mapped to a ASCII code, no? So meron corresponding number yan. No? Like for example, capital letter A is I think ASCII code 65, no? So may mga numbers yan. Pero dito, for our own purposes, we are just going to create a mapping. No? So i-map natin yung A, B, C hanggang Z, tapos yung itong space, no? Blank space, into numbers 0 to 26. So pag may mapping na tayo, yung ating message, i-convert na natin yan into numbers. Okay, so ito yung mangyayari. So this is a secret message. So itong letter T is 19, no? Letter H is 7, I is 8, S is 18. Tapos yung space is 26, no? Balik tayo dito, 26, no? Okay. So once na nakuha mo na yan, ipapad natin with 0, no? Yung number na less than 10, no? For example, itong 4, lagyan natin ng padding na 0. Okay, to the left. So ganito yung magiging itsura niya. Katapos, to conserve, we can group them into blocks, no? Into blocks. So, for example, itong blocks of 4, no? So, yung 19 and 07 magiging 1907, no? And so ganito na yung itsura ng ng message mo. Tapos, so ito yung message mo, ito yung plain text, no? So yun yung plain text. So kapag sinend mo yan, at ma-intercept yan ni Eve, then Eve can just map it back to the original letters and she will know that this is a secret. Now, we want to encrypt this, no? Using RSA. So for each number, we are going to raise this to the exponent e and get the remainder. No? If we divide it by n, which is yung ating composite number, then the result of that will be the encrypted text, no? Or also known as the cipher text. Okay, so ganun siya, no? So this kind of operation is called modular exponentiation. So modular exponentiation is one of the core core functions sa Shor's algorithm. Modular exponentiation. Okay. So if we are not yet familiar with the mod operation, ito lang yun, no? So, ang ibig sabihin lang yan, so for example, if A is equal to 10, no? Ito yung letter mo. And then yung if you define the exponent to be 7, so ito yung makukuha mo, 10 to the 7. No? And then you just divide the result by 17 to get this divide the result by 17 and get the remainder. Sorry. Yeah, divide the result by 17 and the remainder is 5. No? Ibig sabihin, 10 to the 7, mod 17 is 5. So, ganun siya. So, in Python, since we are going to use Python in our lecture series, ito lang yan, no? So 10 raised to the 7 mod 17. So kuha mo kaagad 5. Okay. Now, some example, no? So let's say we choose P and Q, no? 53 and 59. And then, so these are the two prime numbers. No? And secret yan. No? You cannot divulge the prime numbers. Okay. Ang ida-divulge mo lang is yung P times Q. Okay? At yung exponent mo, 7. No? So E and N, ito yung public key. So public knowledge. Pero P and Q is your is part of your private key. No? It's private siya. And if P and Q, if N is actually very big, no? So it's a very big number, like 2 raised to the 2048 bit, no? It's a number with 600 zeros, 1 followed by 600 zeros. Then to factor that out, there is a paper which says it takes about 300 trillion years, no? To factor that out, which is greater than the what you call this, the age of our universe. Okay. So ang gagawin natin ngayon is itong 1907, no? This is one of our plain text. I-erase natin yan to the power 7 and get the remainder, no? If you divide it by 331 to 7, the remainder is 794. No? Lalagyan natin ng 0. Okay. So ganun siya. So it is the number we give to the recipient of the message. Okay. So we can use a for loop, no? To generate the cipher text. No? So doing this, we will get this now. Let me see. Meron ako ano dyan eh. Saan yung aking Python code? Hanapin ko lang, nawala. Andito yata. Okay. I'm not sure if this is big enough, no? I think it's not big enough. Okay. Maybe it's big enough na, no? So cut, encrypt. So ito yung ating ano, ito yung sila, no? 1907 hanggang 064. So ang gagawin lang natin, piprint lang natin kapag in-encrypt na natin ano yung magiging ano. So ang formula is this one, no? So the number raised to the power 7 modulo 3127. Ganun siya. So Python. Yan. Yan. So 794. So, tapos 1095, no? So titingnan natin. So ito yun, no? So yun yung ano, encrypted text natin. So ngayon, pag nakuha na yan ni Bob, so si Alice nagpadala kay Bob, ang si Bob pala nagpadala kay Alice, no? So pag nakuha na yan, si Alice can decipher it, no? Using a key which she keeps private to herself. So the key, D, is the inverse of E, modulo P minus 1, Q minus 1. Okay. Kaya very, very important na yung P and Q should remain private, no? Kasi kapag nalaman yan ng iba, then they will just do this, no? Subtract minus 1 to P, no? So do a P minus 1, Q minus 1, and then take the inverse modulo of E, okay? In this to compute for the private key D, no? So ibig sabihin, kapag nakuha itong B, ito yung ating ciphertext, no? So pag nakuha na yan ni Alice, tapos meron siyang D, she will just raise this to the power, so B raised to the power D, okay? Tapos modulo N. Tapos she can now get the original message A, no? So how do you compute the inverse, no? How do you compute the inverse of E, no? Modulo P minus 1, Q minus 1. So ito yun, no? So E times D, modulo P minus 1, Q minus 1 is equal to 1. Kaya nga inverse kasi if you multiply E times D and you get 1, ibig sabihin D is E to the minus 1, no? So let me see if I can annotate, no? Okay, ibig sabihin E multiplied by E to the minus 1 is equal to 1, di ba? So ito yung ating D. Okay. Okay. That's good. Now, let us remove that annotation. Okay. So using Python, we can compute for D, no? This is a naive Python program, no? So meron kang P and Q and E7. Tapos you compute for the P minus 1 times Q minus 1, no? This is also known as the Euler's tocient, no? Tocient, no? Although hindi ko lang siya kasi ang dami na nating jargon mamaya, no? So let's try to keep this basic, no? So paano mo i-compute yung yung inverse, no? So ang gagawin mo, i-multiply mo yung E and D, no? So i-multiply so magpo-for loop ka from 1 up to this number. Tapos so kasi hinahanap mo yung result na kapag multiply mo itong dalawa, yung E mo at yung D, no? So D is from 1 up to this number. At pag kinuha mo yung modulo, ang magiging result niya is 1. then that is the inverse, no? I mean, ang value ng D is the inverse. So for this case, if I do a for loop, no? Nakuha ko, so this is a for loop from P minus 1 to Q minus 1, no? So that is, ano ba yan? Tingnan natin, no? Python, no? Anong oras na ba? Oh, 6:30, no? Okay, 6:30. Baka, so, sandali lang. Baka meron na ako dito. Anyway, so ito yung makukuha mo na. Pero actually, ang makukuha mo rin siya. Mali yung formatting ko, no? So, if you do power E raised to the minus 1 modulo this one here, it will give you 431. No? So let's say P so Python, okay? P equals 53, no? Tama ba? Q equals 59. Q equals 59. E equals 7. Okay? So if you want to get the inverse of E with respect to modulo and natin is P minus 1, okay, times Q minus 1. Okay? Yan. So let's get the inverse now. What is power of E minus 1? 431. So this is, we get the same value now. Okay. So now, so yung 431 is our private key. Now, kapag, ito kasi yung message na binigay sa atin, di ba? So if we raise that to the power of 431 and get the modulo 3127, ito yung makukuha natin. So let's do that. 0794, okay, actually, POW, okay, 794, raised to the power 431, okay, and then modulo 3127. So 1907. So 1907, that is the plain text, no? Ito yung sinend sa yeah, ito yung original na yung in-encrypt natin. Okay? So now we can apply this to the entire ciphertext using this Python for loop, and we will be able to get the value. So we will get this now, which is our original full message. So let's do that. So ito lang yun. Cut, decrypt. Okay. So yun yung ating Python. So Python, yan. So 1907, so 0818, 0604. So yeah, ito siya. Okay. So that's how we encrypt in RSA now. So it's just a matter of mapping back these numbers to letters to get the message. Okay. Now, so what if, so ibig sabihin si Alice, okay, will really have to keep her key private, no? Hindi pwede na ma-steal ng iba, no? So assuming na it's really impossible to, so one way kasi to steal is to be able to gain access to the machine of Alice, no, and be able to read the private key, no, na nakastore dun sa kanyang computer, no. So assuming it's impossible to do that, no, how can a hacker hack the RSA? So there is another way, no? There's another way, but you need to have great computational technological technologically advanced, no, or meron kang quantum computer to decrypt it, no. And how is it done, no? It's done by what is known as the period finding. Okay, so yung period finding is meron kang so nakuha mo na ikaw si Eve, di ba? Eve, the eavesdropper, no? So nakuha mo na yung B, which is the encrypted text. So paano mo makakrak yung plain text or yung ciphertext pala, paano mo ma-convert into plain text without knowing the private key, no? So ang gagawin mo is to compute for the period. So what is the period, no? The period is the smallest integer that will satisfy this relation. So nakuha mo yung B, which is the encrypted text, you raise it to the power R, and it will give you 1, then that is the period. Ang tanong lang, how are you going to get that period, no? So magfo-for loop ka na naman ngayon, no? In order to find the period R. Yun nga lang, wala siyang shortcut, no? Wala siyang shortcut na kagaya kanina na I can get the inverse, no? I can get the inverse of a number modulo n. Pero dito kasi I want to get the exponent, no? If I get to get the exponent, that will give me a 1, no? So if that's a very hard problem, no? Okay, so ito yung this is the thing na kailangan na natin ng quantum computer, no? So period finding. So let us say nakuha mo na yung period. What will you do? Ang gagawin mo is to compute for the inverse of the exponent. Ito yung isa sa ating private public key, di ba? Public yan, public knowledge. So meron kang E at na-figure out mo yung period, then you just get the inverse of E modulo R, modulo the period. So once nakuha mo na yan, then ang gagawin mo lang is yung encrypted text, you raise that to the D prime, you will get the plain text. So that's how period finding works now. So in our previous example, meron kang ganito, tapos ginamitan mo ng okay, sorry. Nagkamali ako dito, no? Hindi yan. That's not part of the public key. Public key is ito lang, no? Itong 3127 and E, no? So I will have to take note of that, no? So the plain text is ito yung plain text, tapos ciphertext ito. Ang gagawin natin is let's compute for the period, no? So ito yung pinakauna nating nakuha, no? Let us say pinakaunang block. Nakuha natin, no? Encrypted yan. So i-compute natin yung R, no? What is the value of R that will give you 1? Okay? So modulo 3127. So using this Python script, no? We can compute for that value. So andito yata yan sa aking period finding, no? So ito siya, no? So n natin is 3127. At ito yung ating so lang natin Python period finding, no? So nakuha natin na R is equal to 58, no? R is equal to 58. So P is equal to 1 when R is equal to 58. So, balik tayo dito. So 58 yung hinahanap natin, which is the value of R. So, ang gagawin natin ngayon is we are going to compute for the inverse, compute for the we can compute for the following equation. So, itong equation na to will be satisfied, or actually, ito, yung nga, compute for the inverse. So, compute for the inverse of E. So, this will be satisfied when M is equal to 3 and D is equal to 25. So, ito yung hinahanap natin. Okay? So, ito yung hinahanap natin. And then, ang gagawin lang natin is you raise this to the power 25, modulo 3127, at makukuha mo na yung original message mo. Okay? So, that's period finding. Okay? So, that's good, no? Now, I only have 20 minutes to walk through the why it works, no? So, it's important that we know why it works. Kasi para siyang magic ngayon, no? And we don't like, as much as possible, we want everything to be klaro, no? Bakit gano'n, no? Bakit gumagana siya? Okay. So, let me go to the next slide. So, ito na yung the RSA theory. Okay. So, wag na natin i-review kasi alam na natin to, no? Okay. Ito siguro, review lang natin to, no? So meron kang so meron kang plain text, raise it to the power C, modulo PQ, it will give you a ciphertext B. Okay. And then, meron kang, pag nakuha na yung ciphertext, raise it to the value of the private key, and then you'll get the original message. So that's how it works. Okay. Okay, so meron din akong ibibigay sa inyong exercises. Okay. Dito pala. Let me show this first. No? So, ibibigay ko yung exercise na to sa inyo. No? So, meron akong secret message. No? Well, actually, magbibigay ako talaga ng exercise na may yung hindi nyo alam yung secret message. No? And I want you to decrypt it, no? Using the RSA. Okay. So, na-cover natin the period finding. No? So, what's the purpose of this lecture, this slide? The purpose of this is we want to understand, no? Bakit nadi-decrypt ng private key yung ciphertext? And we also want to understand bakit gumagamit tayo ng modulo P-1, Q-1 and not P times Q, no? To compute for the inverse of C. Okay? So we want to remove that mystery, no? So where C is ito yung exponent mo, no? Tapos, bakit you compute the inverse of D in modulo R, no? And not in modulo P-1, Q-1, no? So we want to learn those things, no? Okay. So let's go into theory first. So, yung lecture kanina ni Jeff, mabigat na yun eh. So, baka ano, no, baka yung iba sa atin na ano na rin, no, nabangag na rin. But don't worry, no, you can always review this recording. Okay, so let's begin with the theory, no. Now, dito ginagamit yung tinatawag na group theory, no. So it's a mathematical concept, no, that is useful in a lot of places, no, especially in physics. So group theory. Dito gagamitin din natin siya, no. So the concept of group is used in both the RSA and the elliptic curve. Pero hindi natin i-discuss yung elliptic curve. I-record ko na lang yung aking lecture, no. Okay, so a group is nothing but a set together with an operation, no? Multiplication operation, no? Called the group law, or the group multiplication, group operation, such that when you combine two elements using this operation, you get another element, no? Which is denoted by A dot B or AB. Now, to qualify as a group, yung set, the set of this, the set comprising of these elements, and the group G must satisfy 4 known axioms, no? Group axioms. Number 1 is closure. Ibig sabihin yan, if you multiply A and B, then it should also be an element of G. No? So parang ano lang yan, no? Multiplication, no? Like let's say reproduction, no? When you have when rabbits, you know, they multiply, they give birth to a rabbit as well, no? So kaya closed yung operation na yan. Kapag rabbit, you know, reproduces with another rabbit, no, and gives a horse, hindi na yan closed. Associativity, so it doesn't matter kung paano mo kinuha yung ginawa yung multiplication, no? Pwede mo unahin yung A times B, or pwede mo unahin yung B times C, you will still that will still be valid. Tapos meron kang identity element. So kapag meron kang isang element, kapag in-apply mo yung group operation, it will give you the same so for example, sa element A, it will give you A itself, no? Kasi yung E is identity element. And meron tayong inverse, no? So this is very important, no, sa ating discussion, no? The inverse must exist. Kaya group dapat siya, no? So kanina I mentioned about the private key, no, as the inverse of the public key, modulo P minus 1, Q minus 1, no? So dapat importante na may inverse exist. So, ibig sabihin, if you have A and B, and then if you multiply them together, it will give you the identity element, then A is an inverse of B. Okay. And finally, the number of elements in the group G is called the order of the group. Okay. So, for example, the set of integers now is a group. So it's very common, no? The group is a very common occurrence now. So even the integers is a group now. So we have been using integer siguro without realizing that it's actually a group. It satisfies this important relation. Okay, now let's define the modulo. No? Kanina na define na natin to yan. So given two positive numbers A and N, the A modulo N, or abbreviated as A mod N, is the remainder of the Euclidean division of A by N. So in other words, yung A mod N is the remainder ito, no? Yung R. Okay? So this one is known as the quotient remainder theorem, no? So if you have a number A, then if you divide it by N, it will give you a quotient Q. Tapos, if it give you a quotient Q, tapos may remainder siya, no? R. Okay, this is the first thing that we have learned siguro sa elementary, no? Sa division, no? So meron tayong mga remainders, no? And quotients. Now, let Gn be the set of positive numbers less than n with no common factors with n. Okay? So, n can be any number, no? Tapos, yung G is the set of all numbers na less than n na walang common factor with n, no? So, ilagay mo lahat yun na walang common factor, no? So, for example, if n equals 10, ilagay mo dun yung mga walang common factor with 10, no? So, like for example, 7, okay, 3, no? So, hindi common factor. So, ilalagay mo dun. Tapos, yung set na yan, modulo the n is actually a group, no? And meron exercise dito that will ask you to, to verify that it is a group. So it should satisfy all those properties of a group. Now, ngayon, what happens if P is a prime number and we get the set of all numbers less than P which don't have a common factor with P? Okay? Now, that is very interesting, no? And it makes things very simple. Why? Kasi if P is a prime number, then all of the numbers that are less than P are already part of the group GP, no? So for example, if P is 71, then all numbers between 0 to 70 are part of GP. Kasi prime nga si P, no? So wala siyang, none of those that are below, that are less than P have common factor with P. So in other words, there are 7 P minus 1 elements of GP. And that is the order of GP, no? So the order of GP is P minus 1. Okay. So remember, the order of GP is P minus 1, no? That's the number of elements that are contained in the group GP, where P is a prime number. Okay. Now, suppose A is an element of GP. Okay. So A is an element of GP. Ibig sabihin, A doesn't have any common factor with B. Okay. In other words, co-prime, no? Hindi siya, walang, A cannot divide P. Now, no matter how you multiply A with itself, no? A times A times A times A, the product will never have a common factor with P. Okay? It's a prime number nga si P. And A doesn't have a common factor with P. Okay? So let k be a positive integer, then the set generated by doing all of this exponentiation, no? So pick any number k, and then what you do is you get the exponent, no? So you generate, no? You generate the set, no? A to the 0, a to the 1, no? A to the 2 hanggang k, then modulo n. This one is also a group and is a subgroup of GP. Okay, so subgroup siya, no? It's a group, and it's also a subset of this big set. So for example, if you have A is equal to 3 and K is equal to 6, then you can generate this set, no? So 3 to the 1, 3 to the 2, okay, 3 to the 6, no? So ito yung makukuha mo, ma-generate mong elements, no? Mod 7, modulo 7. And if you do, and you can do a multiplication table, no? Modulo multiplication table. So if you multiply 3 times 3, it will give you 2, no? So modulo 7. Okay. So ito yung kanyang multiplication table. And so this one is subgroup, no? So a subgroup of G G7. Okay. Now let's go to Lagrange theorem. It's very important. Ang sabi dito, if you have a subgroup, no? If you have a group G, and lahat ng mga subgroup of H sa subgroup of G, no? H, let's call them H. Lahat ng mga H which are subgroups of G, kunin mo yung kanilang number of elements, no? Which we call the order of H. That number can divide the order of G, no? So whatever is the number of elements, total number of elements of G, yung number of elements ng H, it can divide the number of elements of G, no? Okay. So that's the theorem of Lagrange, which we are not going to prove here, no? So there's an exercise here, no? Show that there is a positive integer k such that a to the k is equal to 1, no? So, ganito lang yan, no? So, meron kang dalawang integers, m and n, no? Such that m is greater than n. Pagkatapos, suppose a to the m is equal to a to the n. Then, what you can do is just multiply this by the inverse of a to the n, no? Which is a to the n minus 1, and it will give you this. Then and then by the law of exponents, this can be written as a to the m minus n is equal to 1. Now, if you define this to be your k, then you have shown this one here. Okay, so we are going to use this later in our discussion. Okay. Now, the smallest such k is called the order of A, no? So meron kang number and meron kang k, so the generator, you generate all of the possible values, no? A raised to the k, no? Tapos the smallest such number na makuha mo is called the order of A, no? Which is the order of the subgroup generated by A. Okay, order of subgroup, no? So ibig sabihin yan, A raised to the p minus 1 is equal to 1 modulo p, no? So how do we show this? How do we show this? So alam natin na a to the k is equal to 1, no? Now, and k is the order of the subgroup generated by A, di ba? And alam natin na the order of the subgroup by virtue of Lagrange theorem divides the order of the entire group. Okay, so the order of the entire group is P minus 1, di ba? Okay. So which means there is a number, integer m, such that if you multiply this by k, will give you P minus 1. So therefore, a raised to the P minus 1 is equal to a raised to the mk. But we know that a to the k is equal to 1. So therefore, a raised to the P minus 1 is equal to 1. Okay, modulo P. Okay. So ngayon, we are still gathering our tools, no? Our tools. Baka mag-extend tayo ng konting minutes lang, no? Okay. Hindi ko na i-cover yung period finding, no? But I'm going to record that. So ngayon, suppose that A is equal to 1, no? Modulo n for any positive integer k. Then for any positive integer k, no? Since A is equal to 1, then A to the k is equal to 1, no? So what you do to show that is using the quotient remainder theorem. No? Alam natin na A can be expressed as this formula. Okay? So if you square it, then using the so you just square the binomial, it will give you this, di ba? And makikita mo that ang form niya is something like this as well, no? Na merong n, merong 1. Okay? So ibig sabihin, a squared is also 1 modulo n. Okay? So a squared. So if we call this s, so this becomes Sn plus 1, no? Which is has the same form as this one here. So ibig sabihin, a squared is also 1 modulo n. And actually, it also it's the same. Same goes for a to a cubed, no? A to the 4th, no? So that's why a to the k is equal to 1. Okay. Now, let a be a number that is neither divisible by prime numbers p and q. So remember, meron tayong p and q, di ba? Which are private, no? Private. Tapos, let's say we have a number a that is neither divisible by prime numbers p and q, no? So no matter how many times you multiply a to itself, it will not still be divisible by p or q, no? So in other words, a is therefore an element of two groups, g of p and g of q. Di ba? Now, in particular, di ba, naalala mo, meron tayong napakita kanina na, sorry. So, sabi nga dito, no matter how many times you multiply it to itself, ganun pa rin siya. So, let's say, I multiply A to itself, Q minus 1 times, no? So, ito siya. Now, since wala pa rin siyang factor in common with GP, then it's an element of GP. Okay? So, wala siyang factor in common with P, so it's an element of GP. Okay? So, therefore, dito sa equation 2, okay, itong P minus 1 natin, okay, if we substitute, AQ minus 1, okay, sa A, then we will get this one here. AQ minus 1 raised to the P minus 1 is equal to 1 modulo P. In the same way, ganun din, no? Na we can also show na A raised to the P minus 1, okay, raised to the Q minus 1 is equal to 1. Ngayon, mod Q naman, no? So, modulo Q naman siya. Dito, modulo P. Okay? So, what does that give us, no? So, this means that equations 4 and 5 mean that so what does this mean? So A raised to the P minus 1 times Q minus 1, no, by the law of exponents is equal to 1. It means that there is a number M such that if you multiply by PQ, so let me show this now. So in other words, meron tayong okay. So A raised to the P minus 1, Q minus 1, okay, is equal to 1, di ba? So this one is equal to some number, ano ba yung sinabi ko dito? Some number M multiplied by PQ plus 1, no? Pagkatapos, if you transpose this here, that will give you the minus 1. Okay? So, ibig sabihin lang yan, this one here is divisible by both P and Q. Okay? Ito. So, yun nga, no? Napakita na natin the, if you remember this one is nothing but the quotient remainder theorem, no? Quotient remainder theorem. Okay. So in other words, ganyan siya. So ganito siya. Okay. Now let me erase this. Okay. Okay. So andito na tayo, no? Now from exercise 6, if S is a positive integer, we can raise equation 6 to S, no? So remember na meron tayong exercise 6 dito. Exercise 3 pala. Ito exercise 6. Na if A is equal to 1 modulo N, then we can raise it to any power and it will still be 1 modulo N. No? So this means na because this one is equal to 1, then we can raise it to any power and still get 1. Okay, modulo PQ. Now, what power is that, no? Let's say we raise it to the power S. If we raise it to the power S, ito yung magiging itsura niya, no? Okay. It's equal to 1. If you multiply both sides by A, this will give you this one here. No? Multiply both sides by A. So that this becomes, by law of exponents, this becomes A raised to the, so dadagdag mo dito plus 1, no? Is equal to A. Okay. But what is this expression? Ano expression na to? Okay. Also, we are going to use this pala, no? We are going to use this later. Let's remember this one. Okay. Now, let's see an element of this group, no? So, meron tayong group na the group of all numbers such that they are less than P minus 1 times Q minus 1, and they don't have a common factor with P minus 1 times Q minus 1. So ito yung group nito. And let C be an element of that. Now, it's because C is an element of that, and sorry, an element of that group, and that is a group, no? So this means that C has an inverse, no? By virtue of this one being a group. Okay, group kasi siya, then meron siyang inverse, no? Yung C. So in other words, C times D, if D is the inverse, then C times D is equal to 1 modulo P minus 1, Q minus 1. Okay? So now, pag nakita mo to, ang ibig sabihin niya, you can apply the what's the theorem? The quotient remainder theorem. You can apply the quotient remainder theorem. So there is an S such that CD is equal to S multiplied by this one here plus 1. Okay, so this one is the quotient remainder theorem. But by equation 8, remember equation 8, ito, that is nothing but A. Okay? So, ano siya ng CD, no? So, A to the CD is equal to A. Okay? So, so alam natin na yung ating ciphertext is A to the C, di ba? Remember? Yung ciphertext natin is A to the C. So if we substitute B here, no, into this equation, so A to the CD, so B to the D, A to the C is B to the D, okay? But B is the ciphertext. So B raised to the D is equal to A. So in other words, this is how the decryption works. So ganon gumagana yung RSA. Okay? Now, since we already got past 7 o'clock, yung period finding, I'm going to just record this. Okay? So, and I'm going to send you an exercise, no, in the Discord, just to exercise your programming skills. So bibigyan ko kayo ng isang encrypted text, and I would like you to give me the decrypt it, no, using RSA. Okay, back to you, Steph.
All right, thank you so much, Sir Bob, for sharing your presentation. And ibibigay lang naman ni Sir Bob sa Discord yung continuation ng lecture niya. All right, so allow me to share my screen po. Thank you, Sir Bob.
Thank you.
So temperature check muna po tayo. So kumusta naman ang lahat? So on a scale of 1 to 10, how was the session? So can we get an answer? 6, 7, 8, 9. Okay, mostly we have an average of, oh, may 9 naman. All right, so at this juncture, we are reminding you guys to join the Xqubit na project. So kindly screenshot this one or scan the QR code, and we are looking forward sa mga entries niyo po. So let's do a photo op, requesting everyone to open their cams para naman makikita natin ang magaganda at handsome na ating mga participants. All right. So let's wait for everyone to open their cameras. All right. Sige. So I think I have 1, 2, 3, 4. Okay. So if you cannot open your cam po, you can do a quick reaction, heart, thumbs up. All right. So shall I count po? And I count to 1, 2, 3, smile. Next page. 1, 2, 3, smile. And another one. 1, 2, 3, smile. All right. Thank you so much. And for the attendance link po, here is the attendance link. Code 2684. All right. And we will also send the attendance link naman po sa Discord. And the rest, if you have any more questions, just direct your questions dun sa ating Discord channel. Thank you so much po everyone for joining, and see you po next Saturday, and hopefully sa hackathon po makaka-join kayo. Okay, good night. Yes, Sir Bob?
Na-mention mo ba yung hackathon?
Yes
Kung-
po, sir.
Okay.
Yes.
Okay.
Okay. Thank you so much,
Okay,
everyone.
everyone. Thank you.
Thank you. Good night. Good evening. Okay. Attendance link will also be sent po sa Discord. Thank you.